Today we are going to give a brief introduction to low density parity check codes. So, we will start off with very basic definition of what do we mean by a low density parity check matrix, what do we mean by low density, and then we will show how we can write the parity check matrix using a bipartite graph which is known as Tanner graph. Then we will talk about what is a regular LDPC code, and we will give some few simple constructions of regular LDPC code. Then we will talk about irregular LDPC code, and again we will give some very simple construction of irregular LDPC codes. So, what do we mean by low density? So, we will first define what do we mean by density. So, a density of a source is basically the expected number of ones in the source. Now, when is it a low density? Now, a source is low density or sparse if the density of 1 is less than 0.5. And we say a vector is very low density or it is low density if the density vanishes as the length of the vector increases. In other words, number of ones are fixed even if we increase the length of the vector. In that case, the density will vanish as length increases. We will also define a term which is called an overlap. So, if you have two n tuples, we call an overlap between two vectors as the number of positions in which the ones are common. So, for example, if you have a vector, let us call it V0, which is 1 0 0 1 1 0 1, and you have a vector V1 which is 1 0 1 0 1 1 0, then we can see there is an overlap here in one location, two location. So, there is an overlap of 2. So, what is a low density parity check code? As the name suggests, a low density parity check code are specified by a parity check matrix which is of low density. And what do we mean by low density? So, the number of ones in this parity check matrix is very small, it is less than half. So, an LDPC codes are specified by a parity check matrix which consists of mostly zeros and very few ones. Now, what is a regular LDPC code? A regular LDPC code is defined by these three parameters. This is the code length, this is number of ones in the columns of the parity check matrix. So, a regular LDPC code has same number of ones in each of the columns of the parity check matrix, and that number is given by W subscript C. Similarly, W subscript R gives us the number of ones in each of the row of this parity check matrix. Again, for a regular LDPC code, the number of ones in each row is same. So, a regular LDPC code is specified by this block length n and number of ones in each of the columns and number of ones in each of the rows. So, we can describe it by a low density parity check matrix of M cross n, where each column has a fixed number of ones, and that is WC3, and that has to be greater than 3. This has to do with distance properties of LDPC codes, and each row has WR number of ones, where WR is greater than equal to WC. In other words, now what do the rows in the parity check matrix specify? Now, if there are WR ones in rows of the parity check matrix, it specifies that WR bits are participating in a parity check equation, and in all the parity check equations the same number of bits are participating. And what is the implication of WC once in each column? It means that each bit appears in W sub C parity check equations. So, each bit participates in WC parity check equations. So, that is what I am saying here. So, each parity check constraint in a regular LDPC code will have WR code bits, and each code bit appears in WC parity check constraints. Now, typically the number of ones, because it is a low density parity check matrix, so numbers of ones are much less than the dimension of these matrix, and WR is also much less than n. Number of ones, we can count it column wise, there are n columns and there are WC ones in each column. That number should be equal to number of rows multiplied by number of ones in each row. And number of parity check equations is at least equal to n minus k. So, the rate is at least 1 minus WC by WR. Sometimes we do have some redundant parity check equations in the LDPC parity check matrix. This is one example of a low density parity check code. You can see in this matrix most of the entries are zeros. These are all zeros, these are zeros, these are zeros. You can see most of the entries in this matrix are 0, very few are ones. And you can see that each row, let us look at row number 1. Row number 1 has 4 ones, row number 2 has 4 ones. You can check any row, you can check, let us say this row. This has 1, 2, 3, 4, there are 4. So, each row of this low density parity check matrix has 4 number of ones. So, WR in this case is 4. And each column, let us take column 1, there is a 1 here, there is a 1 here and there is a 1 here. So, column weight is 3. You can check any column, look at this column, 1 here, 1 here and 1 here. So, column weight is 3. You can take this column, there is a 1 here, there is a 1 here and there is a 1 here. So, the column weight is 3. So, WC is 3, n is 20. You can see there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So, the block size is 20 and this is full rank. So, the rate here is 1 minus 3 by 4, which is a rate 1,4 code. So, this is an example of a low density parity check code. You can see the fraction of ones is much smaller than number of zeros. Now, we can represent these parity check matrix using a bipartite graph, and this bipartite graph representation of parity check matrix of a linear block code is known as Tanner graph, named after Michael Tanner. So, what is a bipartite graph? In a bipartite graph, the nodes can be partitioned into 2 classes. Now, what are those 2 classes? What is the property? That no edge can connect nodes from the same class. So, when we partition the nodes of this graph into 2 classes, there is no connection between nodes within a class. So, if you want to reach another node within a class, you at least have to have a travel twice. Okay. So, a bipartite graph is one where I can separate out the nodes into 2 classes such that there is no edge connecting nodes in the same class. Now, we can draw a bipartite graph for an LDPC code parity check matrix. So, a Tanner graph, and that is basically known as Tanner graph. So, Tanner graph for an LDPC code is a bipartite graph which has the property that there are two sets of classes of nodes. One class of nodes which we call variable nodes, they represent the n bits of the code word, and the other class is what is known as check nodes. They represent these m parity check equations. And how do we connect an edge? An edge connects a variable node to the check node if and only if that particular bit participates in the parity check equation. So, let us take an example to illustrate how we can draw the Tanner graph of an LDPC code. So, this is an LDPC code, block n is 12, number of ones in each column, you can see 1, 2, 3, that WC is 3, and number of ones in each row is 6, you can check 1, 2, 3, 4, 5, 6. Each row has 6 ones, each column has 3 ones. Now, how do we draw the Tanner graph of this? So, as I said, there are two classes of nodes. One class of nodes for the variable nodes. And how many variable nodes we have? We have 12 variable nodes. So, let us just draw 12 variables node. 1, this 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let us just label them. Let us just label them as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11. And then you have how many parity check equations? 1, 2, 3, 4, 5, 6. So, we will have the next set of nodes will be for parity check equations, and there are 6 of them, 4, 5, 6. Okay. Let us just label these bits, that will be easier for. So, let us just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now, let us and similarly label these parity check equations. This is, let us say, 0th parity check equation, 1, 2, 3, 4, 5. So, let us look at this one, this 0th parity check equation. Now, which are the bits that are participating in the parity check constraint? Bit number 0. So, we will draw an edge from bit number 0 to this parity check constraint. Bit number 1, that is this. Bit number 2, that is this. Bit number 5, that is this. Bit number 6, that is this, and bit number 10. Okay. So, this is my first parity check constraint. Let us look at now this one. Which are the bits participating? Bit number 0, bit number 0, bit number 1, bit number 1, bit number 2. So, there is an edge from bit number 2 to this parity check constraint. Bit number 3, that is this. Bit number 4, that is this. And then you have bit number 11. So, you have this one. Okay. Now, look at this parity check constraint. Now, which are the bits that are participating? This is 5. So, that is here. 6, that is this one. 7, that is this one. 9, that is this one. Then 10, that is this one, and then 11, that is this one. Okay. Similarly, for this parity check constraint, bit number 0 it's participating. So, you have a edge from here to here, then bit number 3 is participating. So, there is an edge from here to here, bit number 7 is participating. So, there is an edge from here to here, bit number 8 is participating. So, there is an edge from here, bit number 9 is participating. So, there is an edge from here to here, and bit number 11 is participating. So, there is an edge from here to here. And similarly, we can do for this. I will just do it. This is 1, 3, 4, 6, 7, 8. That is it. And this finally, this parity check constraint, bit number 2, bit number 4, bit number 5, bit number 8, bit number 9, bit number 10. So, this is the Tanner graph representation of this low density parity check code. Okay. Now, let us define what do we mean by cycle in this Tanner graph. So, cycle is defined as a path consisting of length L, which will start from a node and come back to the same node. So, what is a cycle? So, it is a path cycle of length L is, it starts from a particular node and comes back to same node. So, let us look at this, let us say this node. So, if you start from this node, this edge 1, 2, 3, 4, 5, 6. So, this is a cycle of length 6. Now, note that it is a bipartite graph. So, it will only have even length cycles, because there is no connection between nodes of the same class. As I said, in this particular example, this has cycle 6, 1, 2, 3, 4, 5, 6, and this can be viewed from the parity check matrix also. So, you can 1, 2, 3, 4, 5, 6. Okay. Now, we will define what is known as girth. The girth is the length of the smallest cycle in this graph. So, girth is defined as the length of the smallest cycle in this graph. In this particular example, the smallest cycle is 6. You can see there is no cycle of length 2 or 4. Now, when we are decoding LDPC codes, we would like the girth to be very large, because number of independent iterations that we can get is proportional to the girth of the corresponding Tanner graph of the LDPC code. Now that we have defined what is a regular LDPC code, let us talk about how we can construct these LDPC codes. So, we will first start with random construction of LDPC codes given by Gallagher. So, if n is the block length and m is the number of parity check equations, and if you are asked to design a regular LDPC code with WC once per column and WR once per row, you can follow this procedure. So, divide m cross n matrix, which is your parity check matrix, you divide them into WC m by WC into n sub matrices, such that in each of these sub matrices your column will only have a single one. Next, you start writing. So, in each of these sub matrices, what you do is you write ones in the descending order. So, the ith row will have ones from location I minus 1 WR plus 1 to I into WR. So, what you do is, so I will just illustrate basically. So, what you do is, first you have an M cross N matrix. Now, this was a rate half code, remember rate run by 4 code, remember WC is 3, WR is 4. So, this is 15 cross 20 matrix. Now, what you do is, you divide this 15 cross 20 matrix into 3 5 cross 20 matrix sub matrices, right. That was the first step. Divide an M cross N matrix into WC, M by WC into N sub matrices. So, once you divide them, so this is one 5 cross 20 sub matrix, this is another 5 cross 20 sub matrix, this is another 5 cross 20 sub matrix, and each of these sub matrix should have only ones. And what you do, you start writing ones in the descending order. So, you start writing 1 here from location 0. Now, WR in this case is 4. So, in the 0th row you start writing from column 0 to 3, next row you start writing from 4 to 7, like that you start writing ones. So, that is what I have written here, that first of these sub matrices contains all ones in the descending order, such that ith row contains ones from location I minus 1 into WR plus 1 to I times WR. So, once you have constructed this sub matrix, this 5 cross 20 sub matrix, by putting ones like this in descending like this, once you have constructed this, rest all are zeros. Now, note that each of the columns here have 1 ones, and what about, you can check any column of these sub matrix, it has only 1 1. And note what is the row weight. Now, each of the row here has WR, which is 4 number of ones. You can check, this is 4 ones, you can check here, this has 4 ones here, these are the 4 ones here, you can check this has 4 ones. So, what you have created is, you have created a sub matrix which has column weight 1 and row weight WR. Now, next, to get WC column weight, what do I need? I need to design a similar sub matrix here, which will have 1 in each of the column and WR ones in each row. Now, how do I get this sub matrix and this sub matrix? So, what I can do is, I can do column permutation. So, for example, I can move this column here, I can move this column here, I can do column permutation. Now, when I do column permutation, I do not change the weight of the column, it is still 1, and I do not change the weight of the rows, it is still 4. So, by doing column permutation, I will get this sub matrix, which will again have 1 1 in each column and 4 ones in each row. The same thing I will do for this sub matrix. I will again do column permutation of this matrix, and I will get this sub matrix. So, the subsequent sub matrices are obtained by doing column permutation, and by doing column permutation, I am not disturbing the weight, the row weight or the column weight. The column weight of this sub matrix is still 1, the row weight is still 4. Now, once I do this, then I am able to design these 3 5 cross 20 sub matrices, each of them have column weight 1. So, overall column weight will be 3 and overall row weight is still 4. So, I am able to design a low density parity check matrix, which has 3 ones in each column and 4 ones in each row. So, that is what I said, that other submatrices are merely column permutation of the first submatrix. So, this is Gallagher's construction of a regular LDPC code, which has WC once in each column and WR once in each row. Now, we will talk about simple constructions based on permutation matrix, and these were given by Mackay. You can read this paper, Good Error Correcting Codes on Very Sparse Matrices by David Mackay, which appeared in IEEE Transactions on Information Theory on May 1999. So, one way of designing an M cross N matrix which has WC column weight and WR column weight is you can randomly put ones, ensuring these criteria is satisfied, and also you want to ensure that overlap between two rows of this parity check matrix is not more than 1. Otherwise, you will have cycles 4 and in your LDPC code. Now, next what we are going to talk about is how we can use permutation matrix to design our LDPC codes. So, that is what I am going to show in the next few slides. So, let us define what a permutation matrix. So, a permutation matrix is an identity matrix which is row reordered. So, this is an example of a 5 cross 5 permutation matrix. You can see each row has 1 1 and each column. So, each row has only 1 1 and each column has a single 1, and this is just an identity matrix with row reordered. Now, we could also use a circular matrix to design our LDPC codes. Now, what is a circular matrix? So, a circular matrix has the property that each row is just a circular shift of previous row. So, for example, you take this example, this first row is 0 1 0 0 1. Now, this 0 comes here, this 1 comes here, this 0 comes here, this 0 comes here, and this 1 comes here. So, that is your second row. Now, the third row, this 1 come here, this 0 comes here, 1 comes here, this 0 comes here, and this 0 comes here. Similarly, here this 0 comes here, this 0 comes here, 1 comes here, 0 comes here, and 1 comes here. And likewise, this 1 comes here, this 0 comes here, 0 comes here, 1 here, 0 here. So, you can see each row is a circular shift of previous row. So, we will now show how we can randomly construct these permutation matrix. This is just an identity matrix which is row reordered. Now, we will show how we can construct our LDPC codes using these permutation matrix. So, the first example that we are going to consider is an example of a regular LDPC code. Now, this regular LDPC code has column weight 3. So, WC is 3 and row weight is 6. So, WR is 6. You can see if this is a regular LDPC code because all the rows and columns have the same weight. Okay. Now, how can we use permutation matrix to design this? So, let us take this example. So, let us say you have to design and so what is the rate here? Rate here is 1 minus WC by WR. So, this is 1 minus 3 by 6, that is the rate half. So, M will be n by 2. So, M here will be n by 2. So, what we did was, so this is you can think of as n by 2 cross n. So, what we did was we divided this n by 2 cross n matrix into sub matrices in this particular way. So, this is, so this one that you see, this is n by 2 cross n by 2 matrix, then this is another n by 2 cross n by 2 matrix. So, these are 2 n by 2 cross n by 2 matrices, which are further divided into some matrices n by 6 by n by 6. So, each of them are your n by 6 by n by 6 matrix. And what does this signifies? This signifies that this is a notation that we are using to denote a permutation matrix. So, this is one random permutation matrix, this is another random permutation matrix, where the location of one is different from what was here in this particular matrix. So, this is another random permutation matrix. So, these ones that you see here, these are all random permutation matrices. Okay. Now, note that we need a column weight of 3. Now, if we stack 3 permutation matrices like this, now each of these permutation matrices has 1 1 in its column. So, overall we will get column weight 3, and if we stack 6 of them like this, then each row also has 1 1. So, we will get overall 6 ones in each row. So, this way we can generate a LDPC code with these parameters, column weight 3 and row weight 6. Now, the same thing can be generated using by overlapping of random permutation matrices. Now, what do I mean by overlap of random permutation matrix? So, let us say you have a permutation matrix and you add another permutation matrix. Now, please note, you ensure that there is no overlap between ones in this matrix and this matrix. If you add these two permutation matrix, what will you get? You will get a matrix which will have 2 ones in each row and 2 ones in each column. Now, if I add another permutation matrix and I ensure that the one in this permutation matrix does not overlap with ones in this matrix, which I got by adding 2 permutation matrix, then the resultant permutation matrix that I will get will have row weight 3 and column weight also 3. So, another way of designing this LDPC code is by overlapping of random permutation matrices. Please note, when I overlap them, I have to ensure that there is no ones that are getting overlapped, then only I will be able to retain the weight. So, if I overlap 3 such random permutation matrices and I ensure that there is no overlap between the ones in each of these 3 random permutation matrices, then what I will get is a matrix which will have 3 ones in each row and 3 ones in each column. I can construct another n by 2 by n by 2 matrix, this one, which is again by overlapping of 3 different random permutation matrices, ensuring that there is no overlap of ones. I can get another matrix which will have 3 ones in each row and 3 ones in each column, and this will ensure that each column of this matrix will have column weight 3 and each of the rows of this matrix will have row weight 6. So, this is another way I can use the permutation matrices to construct my regular LDPC code. Now, let us talk about what is an irregular LDPC code. So, in irregular LDPC code as opposed to regular LDPC code, the number of ones in each column and number of ones in each row are different. So, we will have to specify the degree, the node distribution, the column node distribution as well as the row node distribution. So, for an irregular LDPC code, we define the distribution of column nodes as well as row nodes according to some distribution. So, what is the degree distribution? We define the degree distribution by this polynomial, which has a property that gamma 1 is basically 1. So, these are the fraction of nodes with degree I. Now, an irregular LDPC code, we have to specify two degree distribution. One is the column degree distribution, other is the row degree distribution. So, the column degree distribution we are denoting by lambda x, and the row degree distribution we are denoting by rho x. So, this is my column degree distribution, this is my row degree distribution, where lambda I is the fraction of edges incident on the variable node which has degree I, and rho I is fraction of edges incident to the check node with degree I. So, let us take an example to illustrate this. Let us just see if we use the same degree notation to represent this. So, the column row distribution is defined by lambda x. Now, here all the columns for the regular LDPC code, all the columns have weight 1. So, then lambda I here is 1, and we will define x raised over I minus 1, and I degree here is 3. So, degree distribution for the column for this regular LDPC code will be x square. Similarly, the row distribution here is, because all the nodes have row weight 6. So, this will be x raised to the power 6 minus 5 x 5. So, that is how we are writing the degree distribution. So, again have a look at the degree distribution. This is a fraction of nodes with degree I, and this is a fraction of nodes with degree I. This is the row degree distribution, this is the column degree distribution. Let us take this example. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So, n is 12. Okay. N is 12. Now, what is column degree distribution? So, this is basically each node participating in how many parity check equations. Let us look at this node. How many parity check equation it is participating in? 1, 2, 3. So, let us just, so this is participating in 3 parity check equations. What about this? It is participating 1, 2, 3. So, it is also participating in 3. This is participating in 1, 2, 3. This is participating in 3. This is participating in 1, 2, 3. This is participating in 2, 1, 2. So, there is one node which is participating in 2. What about this? This is participating in 4, 1, 2, 3, 4. So, there is one node which is participating in 4. This is participating in 2, 1, 2. This is participating in 3, 1, 2, 3. So, this is participating in 3, 1, 2, 3. It is participating in 3, 1, 2, 3. It is participating in 2, 1, 2. And this is participating in 1, 2, 3, 4, 5. Okay. So, then how many nodes are participating in 2 parity check constraint? That is 3. So, what is the fraction? That is 3 by 12. They are participating in 2 parity check constraint. There are 7 of them which are participating in 3 parity check constraints. So, fraction of them is 7 by 12. Then this is 1 by 12 and this which participate in 4 and then 1 by 12 which participate in 5. So, then what is the column distribution? So, this fraction is 1 by 4 x raised to power 2 minus 1, that is x, plus 7 by 12 x raised to power 3 minus 1, that is x square, plus 1 by 12 x raised to power 4 minus 1, that is 3, plus 1 by 12 x raised to power 4. So, this is the column degree distribution for an LDPC code which is described by this Tanner graph. Similarly, we can find the row distribution. Let us look at parity check constraints. So, let us look at this parity check constraint. So, here 1, 2, 3, 4, 5. So, there are 5 nodes which are participating in this. What about this one? 1, 2, 3, 4, 5, 6, 7. So, there are 7 bits which are participating in this. This one 1, 2, 3, 4, 5. So, there is 5 of them. Then here 1, 2, 3, 4, 5, 6. So, there is 6. This one is 1, 2, 3, 4, 5, 6, 7. And this one is 1, 2, 3, 4, 5, 6. So, you can see out of these, and what is the total number of parity check equations? These are 6, 1, 2, 3, 4, 5 and 6. So, then fraction of parity check equations where 5 bits are participating is 2 by 6, and same is the ratio for 6 and 7. So, then we can write the row distribution as 1 by 3 x raised to power 5 minus 1, that is 4, plus 1 by 3 x raised to power 6 minus 1, that is 5, plus 1 by 3 x to power 7 minus 1, that is 6, and that is precisely what I have written here. Okay. So, to describe a irregular LDPC code, we need to describe these 2 degree distribution, namely the column degree distribution and the row degree distribution. So, we can use a random algorithm to construct an LDPC code. So, we first select a profile that describes the number of rows of each weight and desired number of columns of each weight, and then we need to put a mechanism of putting edges between the vertices in such a way that this constraint is satisfied, that so many number of rows should have so many weight and so many number of columns should have so many weight. So, we can place edges at random subject to the profile constraint, and one way of constructing it is as follows. So, make a list of all columns in a matrix with each column appearing in the list number of times which is equal to its weight. So, if let us say there are 5 columns which have weight 3, so then you will repeat each of these 5 columns 3 times in this matrix. Similarly, you make a list of all rows in the matrix such that in each row is repeated equal to its weight, and then what you do is you map one list which is a list of columns into the other list which is the list of rows by random permutation, making sure that there is no duplication. So, you just create a link from the list of columns to the list of rows, and this way you can construct an irregular LDPC code which will satisfy the degree distribution profile. We can also use random permutation matrices to generate our irregular LDPC code. Again, we are going for a very simple construction. So, we will go with this McKay's construction. So, let us say we would like to design an LDPC code which has column weight such that 11/12 of the columns have column weight 3 and 1/12 of column has column weight 9. So, we are interested in row weight of 7. So, we want each of these row to have weight 7, each of these row should have weight 7, and we want that 11/12 of the column should have weight 3 and 1/12 of the column should have weight 9. So, how can we construct this? Using the construction using random permutation matrices that we have studied. So, again I am splitting up this into, so these are by, so this is my rate half code, so it is n by 2 cross n, each of them are n by 6 by n by 6 matrices, these are n by 6 by n by 6 matrices. Now, note that up to this I am ensuring that each column has weight 3 and each row has weight 5. Now, I need column weight of 11/12 matrices to be 3. So, this is already, I have got 5 by 6 columns, I have got column weight as 3. So, then what I can do is for the remaining 1 by 6 fraction of columns, I split them into 2, and what I do is I have column weight here and then I further split them into, so these are all 0 matrices. So, this you can see this row will have weight 3. So, this will ensure that 11/12 fraction of columns have weight 3, and here you can see this has weight 9. I have added, this is weight 2, weight 2, weight 2, that is 6 plus 3, 9. So, this column, this set of columns will have weight 9, and you can check I already had each row weight up to 5, and now I have this row has weight 2. So, this will be overall weight will be 7, this has weight 0 plus 2, the overall weight is 7, here the overall row weight is 7. So, I am ensuring that the way I split up this matrices, I am ensuring that each row will have weight 7, whereas 11/12 fraction of the columns have column weight 3, whereas 1/12 fraction of the column has weight 9. The same thing can be done in multiple ways. This is another construction. You can see here again I am ensuring that each of the columns have weight 3. So, up to this point you have 5/6 of the column have weight 3. Now, I need another 1/12 column which have weight 3. So, I can do that by placing ones like this. Now, I also have to ensure that row weight is 7. So, how do I ensure? So, I have a 3 here. So, I need a weight 4 here. So, I do it by 1 and 3. So, this is column weight, row weight 7. Here it is 3, this was 0. So, this has to have weight of 4. Now, again this, what are these 3, 4? These are again obtained by overlapping of random permutation matrices, and when we are overlapping, make sure that there is no overlap of ones. Okay. So, you can verify that each row here. So, 1, 2, 3, 4, 5, 6. So, this is 7, this is weight 0. Again here this is weight 7. Each row will have weight 7. So, this is the same profile, different construction. This is another construction, same column weight distribution, that 11/12 fraction of the bits should have column weight 3 and 1/12 should have column weight 9, and row weight should be 7, and you can check it. each of the row here has weight 7 and all of these rows from here to here have column weight 3 and this has column weight 9, 4, 4 and this will have weight 1. So, we can use random permutation matrix to construct irregular LDPC codes as well. Thank you.